This is Lab2, Projectile Motion by James Ashball. As an introduction, in this lab I analyzed data and video observing an object that was thrown and moves like a projectile. The purpose of this lab is to understand how to properly implement computational models to simulate the trajectory of a projectile under the forces of gravity and drag, and to compare that model with real-world data. For the underlying physics principles of this lab. In a vacuum, a projectile is affected by one force, gravity, but in our scenario, the force of drag also has an effect. As you can see on the right, the forces of drag and gravity are shown. If you add those two vector forces together, you can calculate the net force on the projectile. We can utilize the velocity update and position update formulas to accurately update the velocity and position after every time step to predict the object's motion. For a brief preview of the results, I discovered that my computational model that included drag more accurately matched my own recorded data from the tracker software than did the model with the gravity alone. Also, the position versus time graph for both the model and the tracker graph matched closely. Finally, there were slight deviations arising from sources of error, which I will discuss later. The setup of my experiment, I identified the system as the paper ball and the surroundings as everything except the paper ball itself. The initial conditions of this experiment were that the ball is thrown at an angle theta with an x and y component to its velocity. Furthermore, both gravity and drag forces act on the ball. This snippet of code demonstrates the iteration component of my computational model of the experiment. The net force, which in this case is gravity plus drag, is found, and each time step, a new position and velocity is calculated via the velocity and position update formulas. These two graphs are from the output of running the code on Lab2 Python. The graph on the top represents motion that includes gravity and drag, while the graph on the bottom involves gravity alone. The motion demonstrates a trajectory in the form of a projectile for both the model with only gravity and the one with drag included. But the results from comparing the trajectories of my computational model and experimental data with and without drag. The predicted versus observed data match much more closely with the model that includes drag, although both roughly match the experimental data. Sources of error account for deviations. Speaking of possible sources of error, there are two main categories that could have occurred in my case. Firstly, recording errors, in which I had possible misclicks on tracker analysis and did not adjust frames correctly at the beginning and end of the video, causing the computational model to be slightly off from exactly matching experimental data. Secondly, miscalculation mistakes in calculating the initial velocity, which would change the trajectory of the projectile. What does terminal velocity mean in the terms of this experiment? Although none of my velocity versus time graphs accurately depict a situation where terminal velocity occurs, a simple experimental design would be to drop an object from a very large height. There would come a point in the projectile's trajectory that the change in position over the delta t becomes the same. This means that the velocity has become constant, implying that the object has reached its terminal velocity. What if the ball was thrown straight up and with the same initial speed? The ball will take longer to reach the table. This is because with the ball being thrown straight up, the vertical component of its velocity will be larger than it was when it was thrown at an angle, as shown by the calculations on the right. This would cause the time it takes to reach the table to be longer. In conclusion, a projectile experiences a net force of gravity and drag if it is in Earth's atmosphere, and the object's motion can be predicted using computer models. These can help us understand natural phenomenon better. Thank you.